Good morning. I'm myself Dr. Prabhakar Rapaka, Associate Professor. Today I'm going to tell about the CMOS IC Design. The topic name is Frequency Response and Noise. The frequency response and noise is very important in the circuit design analysis in the analog CMOS IC design. So your frequency response can be implemented for different mode of operations of field effect transistors. So your field effect transistor consists of gate, drain and source terminals. So here also frequency response we can obtain for the common base stage, common gate stage, common drain stage, common source stage. So here different mode of operations like source follower, single stage, two stage, folded case. Here different concepts you can observe like common source stage, source follower, differential pair stage, and gain bandwidth products and trade-offs. And also we can observe the statistical characteristics of noise, types of noise, representation of noise in circuits, noise for the single stage, noise power and trade-offs, noise bandwidth. So yeah, generally frequency response can be represented in terms of frequency versus gain or frequency versus gain in dBs. Will give the efficient graphical representation of frequency spectrum of the signal. So here frequency response can be implemented for the two cases. One is low frequency cases and another one is high frequency cases, which is gives the efficient representation of amplifiers like CMOS amplifiers. So for consider the frequency response for the low frequency signals, here we are consider the capacitor values, inductor values and resistor values to calculate the gain or bandwidth, gain bandwidth products, efficiency, frequency versus gain graphical representation. So these are parameters provide the gain, power dissipation and the noise impact. For high frequency case, we are neglected these capacitance values, inductance values, and resistance values. Internal circuit disturbance we are neglected, and we are considered only long frequency duration and long signal duration is considered, and we can observe the gain, power distribution, and noise effects. So these are we can implement for the behavior of the single stage and differential amplifiers in the frequency domains. For high frequency response, analyze for the common source, common gate, and common drain or source follower cases. And also it can be implemented for the cascade stage and differential amplifier stages. So such cases we are considered active mirrors and frequency response for the differential pairs. Next one is metal oxide semiconductor transistors. We are used as an amplifiers. So in these amplifiers we are considered the there are three basic configurations we can observe. So in that configurations also we can observe the different capacitances generated within the material. So they are here common gate capacitance, common drain capacitance, and it is common gate to the source capacitance and common gate to the drain capacitance, common drain to the body capacitance, and common source to the body capacitances. These are four different types of capacitance are existed between the different layers or metals in the MOS devices. So the transfer function of CMOS can be represented by considering the simplified circuits. And in such cases, we are consider the poles zeros to maintain the stability of the circuit. In such cases, we are consider here impedances, input impedance, output admittance, transconductance. That means when we are calculating the low frequency signal uh, frequency response, so in such cases we are consider the internal component effects like internal impedance, internal admittance, and transconductance, and also consider the voltage gain, current gain, right, next to power gains also considered, and internal capacitances also considered. So here, for all these cases, we have considered the stability of the system. So for that, we have to calculate the transfer function. Next one is considered the frequency response representation for the low frequencies, band frequencies, and high frequency examples. So here, first one is considered low frequency, which is nothing but a low pass filter of frequency response. So here, low pass filter of frequency response is high at the zero position, and if you are radial frequency increased, and it is, you can observe here the gain, voltage gain on the y-axis after here up to here it is constant, after at this point here slowly fall down. So this one indicates the low frequency response, the relationship between the frequency versus here voltage gain. If frequency is increasing after certain threshold time, here the gain will be decreased. So that is done in the case of low pass filter. Similarly, consider the band pass filter. In band pass filter, after here you can observe here after sometimes from year to year, suppose here omega naught here omega 1. From omega naught to omega 1 here we can observe, from omega naught to omega 1 we can observe here the band of frequencies. At this band of frequencies, at this band of frequency, maximum signal is existed, and at this portion, before below this one is, and after this one is, the signal is here reduced. So that means in this case, in high pass filter, the band of frequencies passing through the here. At this band only, we are getting maximum signal frequency. So that is the characteristics of the band pass filters. Next one is high pass filter response. Here a high pass amplifier response are we can observe here from after a certain threshold level, here frequencies here constant, and you can observe here gain is constant with respect to the frequency. Here frequency goes on increasing after certain frequency, here the output of our gain is constant. This type of effects we can observe for the low frequency, low pass, band pass, high pass, yeah, amplifiers, frequency responses. So to identify the or to get the more efficient to data in digital circuits, we are applying the Miller effect in these circuits. So here the Miller theorem can be converted here into here. Consider a single impedance can be divided into parallel to Z1 and Z2 impedances, and here X and Y can be represented here X and Y, and we are splitting this signal. We are splitting the impedance of first circuit into split into two circuits. That means your total impedance is equal to your mutual impedance of two individual circuits can be represented in by using Miller's theorem. So this is called Miller effect. To analyze any circuit, we can apply the Miller effect to get the internal impedance of any amplifier circuits. So by considering this, we can observe the impedance, admittance, and poles and zeros and floating of the impedance values we can observe. So here we have to find the stability of the circuit. So in such cases, we have to consider, according to the Miller's theorem, the equations can be represented in terms of pole sign zeros. They are, suppose consider this is the voltage gain represented in terms of A1 by this is the consideration of capacitance. This is also another capacitance. This is also another capacitance. So that means in this case we are consider uh, in this case we are consider the different gains with respect to the yeah different internal frequency components are considered. So that can be represented in terms of your cascade amplifiers. So your cascade amplifier circuit, so up to here this is one amplifier circuit, and this is another amplifier circuit we can represent. So in this case we have to observe the this is the one circuit and this is another circuit, we are appended together, then we can call it as cascaded amplifiers. Where cascading the amplifiers will get the high gain, improved performance and high bandwidth we can observe. Next one is your interaction between the your node side. Here you can observe the different capacitances are existed in the circuit. Suppose this is a C1 capacitance and C2 capacitance and C3 capacitance are existed in the MOS devices. We are consider these capacitances to get the here that effects on the output voltage gain. Next one is here we are consider the different mode of MOS transistors. Here they are a common source stage, common drain stage or source follower, and common gate stages. So now consider here a common source stage. In common source stage, here we are observing the this is the here observe the so common source. Here source is the terminal between input and outputs. So this is a source terminal, and here it is common for both input and output. So this is called as a common source stage. And according to the Miller's theorem, we can write here this input R and values in terms of your input gains and output your capacitance, and you can write as output voltage gain. So this is a circuit according to the Miller system. So here Miller can be written as Z1 can be represented in terms of your Z1 and Z2. So we are splitting this circuit into these two circuits. Similarly, we are also splitting this single circuit into two different capacitances, which follows the Miller's theorem in the common source stage. Like this, we can perform the common drain, common gate amplified circuits. Next one is noise. Here, noise is the unwanted signal here added to the message signal. That means the random process of your message signal with the noise signal can be represented as noise effect. So there are different types of noises are occurred in the signal. So internal noise, so external noise. So here we can observe the different types of noises. Okay, like thermal noise, short noise, so flicker noise. So these are some of the internal noise and external noises. Noise due to the rain, due to the thunderstorm, so due to the temperature, due to external causes, they called as external noises. So, for example, consider your noise is a random process. In this example, you have to consider this is a signal generator. You consider one example. The signal generator generates the noise signal. Generates the signal message signal, and here consider the sound of river. This is a river passing path, and here we are getting some sound of the river that is represented graphical representation in terms of T and x2 of t. So here this is a message signal, this is a noise signal. So we are observing these two signal representations, and the unwanted signal can be we are observed with the message signal. If you are getting this message signal and including sound of river, and we are unpredictable some disturbance we can observe, that is called noise. So here if you long continuous signal you can observe, so that can be detected as a perfect noise signal. Next one is it can be represented in terms of average powers. For long process of long signal, long noise signal can be detected with respect to the average power of the random signal. We can represent it x of xa of t and xb of t. We can predict and we can detect the noise signals clearly. So the average noise power can be represented in terms of 1 by t integration of plus t by 2 to minus t by 2. Here we are v square of t by rl dt. So this is the average power equation for the any signal. So this can be applicable for the noise signal. By using this we can represent the noise pulses or noise total noise signal for the long duration. We can get a particular noise observing in the which is added to the message signal. We can predict and we can detect and we can eliminate that noise signals. So the graphical representation, frequency domain representation of this noise signal can be also we can observe by applying the power spectral density of this noise signal. So that is represented here power spectral density of the noise signal. So here we are consider this noise input noise signal passing through the band pass filter, and this is a band pass signal. And when we are passing through this one is it can be observed the magnitude of the message signals represented on y-axis and t and x-axis. So this is the graphical representation of noise spectrum, and it can be also sampled with particular frequency intervals like f1, f2, f3 up to fn. So we can observe the sx of f, that is the frequency spectrum density of the noise. We can calculate the noise spectrum in any signals. So for example, consider men and women voice signals. Generally you can audible from 20 Hz to 20 kilohertz. So in this case we are considered, so this is the men voice signal representation, and this is women voice signal representation. So here the men voice signal, here noise we can represented from 20 to up to maximum extent of this one. And for women, well, you can observe here maximum amplitude we are getting at low frequency. So that means from 20 Hz to 20 kilohertz total signals are existed. From 20 Hz to 10 kilohertz we are getting men's voice signal very high, and from 10 to 20 kilohertz we are getting women voices very high frequency. So we can observe the spectrum with respect to the corresponding time domain and frequency domain representation of men and women signals. So it can be represented in terms of white noise. We are considered the plain signals. You can observe the spectrum spreading level of this noise is we can represent it with respect to the white spectrum, that is additive white Gaussian noise spectrum. So now we can observe the shaping of this transfer function of the noise. Suppose this is the white Gaussian noise and it is represented the transfer function representation, and it is also y of t. This is x of s of x and this is s of y. When we are considering this input signal and that is passing through the some transfer function block, and we are getting the shaping of the noise signal. We are smoothing the signal and we are getting a proper output and the noise signal we can detect and identify. So similar examples also we can observe. Spectral shaping. So here noise spectrum for the two-sided signals, we are consider the negative side and positive side. We can observe here positive side frequency spectrum densities. So that means the two-sided signals can be also represented in terms of one-side signal by applying the here conversion from two signals into the single signals. So here also you can observe the amplitude representation in two cases: continuous signal case, the sample signals case, discrete signals case, and digital signal case. Also, we can observe the different representations of our two domain signals into single domain signal. So, for example, consider here uncorrelated signals and correlated signals. So, here in figure 1, we can observe. So, these signals are there are x1 of t, x2 of t, x3 of t are the three different uncorrelated signals are combined together. We can observe the total signal is in some random fashion. But in the case of correlated signals, x1 of t is same, x2 of t, x3 of t. If these are added together, then x total of signal is here amplified signal we can observe. So this is the basic difference between uncorrelated signals and correlated noise signals. That means we are continuously getting the noise signals for long time. We can get the proper output noise signal. So these are the steps we have to follow for the noise calculation. For example, consider any signals we can observe. First, to identify the source of noise, and next one is finding the transfer function. Next, third one is apply the here Miller's theorem. Next one is the output spectrum, power spectrum, and convert into the frequency domain signals or time domain signals into frequency domain signals into power spectral densities, which can be observed from the minus infinity to the infinity. Thank you.